So today we are going to discuss about wave optics. So in this chapter we are going to discuss about parameters of wave. First of all, what is meant by wave? Wave is nothing but it is a disturbance created by a source of light in a medium. So this disturbance travel in a medium with some speed. So that disturbance is created by a source, what we know as wave. So light has a dual nature, light has a particle nature, and light has a wave nature also. When light exhibits the properties interference and diffraction, it shows wave nature. And also light has a particle nature also. In photoelectric effect and Compton effect, it shows a particle nature. So in previous chapter, we treated light as a ray. Now in this chapter, we treated light as a wave, and we are going to discuss about interference and diffraction phenomena. In previous chapter, we discussed about reflection and the refraction of light by considering light as a ray. So there are some important parameters about wave, that is amplitude and wavelength, time period, frequency, and phase. So wave is represented by this sine curve. Wave is represented by this sine curve. So here the amplitude is nothing but the maximum displacement of the particle from the mean position. So whenever disturbance is propagating to the medium, the particles of the air medium become to vibrate. They become to vibrate. So this is about a mean position. So the maximum displacement of the particle about the mean position, that what we known as amplitude. So in the wave, the upper part of the wave is represented as crust. This is known as crust, and this is known as trough. This peak is known as amplitude of the wave. Wavelength, the distance traveled by the light wave in one time period, that is called wavelength. The distance traveled in one time period is called wavelength. Wavelength. Okay, this is denoted as lambda, and it is measured in meters or centimeters. Frequency is nothing but number of waves released by a source in 1 second. That is called frequency. So frequency is measured in hertz. Now we are going to discuss about very important term, that is phase. The phase is a physical quantity which gives direction and the position of a vibrating particle. Okay, this is about the phase. This phase is measured in radians or degrees. This phase is measured in radians or degrees. Now let us discuss this phase with one example clearly. In first year SHM, we explained the vibration of the particle, simple harmonic motion of the particle, by taking a circle, that is nothing but what? A reference circle. So this is a P particle. Now the projection drawn from P on any diameter is nothing but this is nothing but Pn. As the particle is moving in a circular motion, the projection n is oscillating about mean position along y direction. This is nothing but what we call, this is phase, initial phase phi. For example, if the particle reaches here, that extreme position, then it completes a phase. N completes phase how much? 90 degrees. 90 degrees. If the p particle reaches here, the projection is at mean position. The projection is at the mean position. Then phase of the particle is nothing but how much? 180 degrees. If the p completes a 3/4 rotation, so p comes here, then that n is at extreme position. So now the phase is nothing but how much here? 270 degrees. 270 degrees. If the p completes one rotation, the phase of the particle, that is n, is nothing but here mean position. So here mean position. So phase of the particle is nothing but how much? 360 degrees. So when we say vibrating particle phase 90, then we can easily determine the position and direction of vibrating particle. Phi is equal to 90 means here what? The position of the n is at extreme position. Next it is moving towards mean position. For the phi is equal to 180 means here the position of vibrating particle is at mean position and it is moving towards extreme position. So next phi is equal to 270 means the position of the vibrating particle n is at a negative extreme position and it is moving towards mean position. Then phi is equal to 360 means the position of this projection is at mean position and it is ready to moving towards extreme position. So that means this phase tells us about position and direction of vibrating particle. It is measured in radians or degrees. For example, this phase tells us if the two waves are starting at the same position and completes one wave, then we say that there is no phase difference between these two waves. Both are starting at same time and both are becomes maximum at same time and both are becomes minimum at the same time. So there is no phase difference between these two waves. So when these two waves are traveling in opposite directions, then we say that these two waves are having phase difference 180 degrees. See this first wave which is starting at the origin and it is moving in positive direction. See this second wave, this is starting at the origin but it is moving in opposite direction. So if the waves are moving along this direction, we can say the phase difference between these two waves is nothing but 180 degrees. So these are called parameters of the waves. So now we are going to discuss interference of light. So what is interference? When two light waves travels in same direction will superimpose each other. At the region of superimposition. As a reason of superimposition, light intensity maximum at some points and minimum at some points. This phenomena of light is called interference. So this is one property of light. When two light waves travel in same direction, will superimpose each other, will combine each other. At the reason of superimposition, light intensity maximum at some points and minimum at some points. This phenomena of light is called interference. So in interference, we discuss about two types of interference: constructive interference and destructive interference. Constructive interference and destructive interference. Right. What is meant by constructive interference and what is meant by destructive interference? Let us discuss. So, in light wave, we call upper part of the wave is called crust. This is crust and this is trough. If the two light waves are superimposed, like this, then this type of interference is called constructive interference. The crust of one wave and the crust of another wave, the trough of one wave, the trough of another wave, these are superimposed each other. Then the resultant intensity of light becomes maximum. This type of interference, what we call constructive interference. If the crust of one wave falls with crust of another wave, then this type of interference is called constructive interference. Right. Next, destructive interference. What is meant by destructive interference here? Suppose this is one light wave. So this is another light wave. They superimpose like this. The crust of one wave is superimposed with the trough of another wave. Then the resultant intensity becomes minimum. So this type of interference is called destructive interference. So in constructive interference, the resultant intensity is maximum. But in the case of destructive interference, the resultant intensity is minimum. So this is about constructive interference and destructive interference. So now we are going to discuss about coherent sources. Two sources are said to be coherent if they release waves with a constant phase difference, and with the same frequency. Then those sources are called coherent sources. So if they release without a constant phase difference, then those waves are called non-coherent sources. For example, This is a slit S1 and this is a slit S2. Here S1 releases a wave. At the same time, S2 also releases a wave. Then the initial phase difference between lights coming from S1, light coming from S2 is 0. The initial phase is constant. So these sources are called coherent sources. Coherent sources. Now we are going to discuss about relation between phase difference phi and path difference. So phase difference phi is equal to 2 pi by lambda into path difference delta. This is very important formula. This formula is nothing but a relation between phase difference and path difference. Very, very important problem. Now we are going to discuss about principle of superposition. So when number of waves incident on a particle in a medium, then the resultant displacement of these waves is the vector sum of displacement of individual waves. So y is equal to v1 right, y1 bar and y2 bar, so on. This principle is called principle of superposition. This is known as principle of superposition. So now we are going to discuss about Young double slit experiment, YDSA. So Thomas Young performed one experiment on the interference of light. So this is a monochromatic source of light. So it releases light waves. So these light waves reaches to two slits S1 and S2 and coming out, and these two light waves are superimposed each other and reaches to point P on the screen. So by the superposition of these light waves, we will see bright or dark bands on the screen. So initially there is no phase difference between these two light waves S1 and S2, but there is a path difference delta between these two waves. The distance traveled by the light wave released from S1 is R1. The distance traveled by the light wave released from S2 is R2. Here R2 minus R1. That is nothing but a path difference between these two waves. So here at point P, there is a dark or bright band is formed, which is at a distance x from center of the screen. So at the center of the screen, always there is a bright fringe is formed. So this fringe is called central bright fringe. And the distance between these slits and the screen, this is screen, is nothing but a capital D. Now we are going to doing some mathematical calculation to find out the resultant intensity at point P due to the superposition of light waves which are coming from S1 and S2. So let us assume as the displacement of light wave coming from S1, y1 is equal to, we write here, a sin omega t. Similarly, the displacement of the light wave which is coming from slit S2, y2 is equal to a sin omega t plus phi. Here delta is the path difference and the corresponding phase difference is nothing but phi. When they superimpose each other, the resultant displacement y is equal to y1 plus y2. So here y is equal to, we write y1 means a sine omega t plus a sine omega t plus phi. So y is equal, we write here a sine omega t plus a into sine a plus b formula this is. So here sine omega t cos phi plus cos omega t sine phi. So y is equal to here a sine omega t plus multiply a with a sine omega t cos phi plus a cos omega t sine phi. So this is the equation we get. Now here in this equation take a sine omega t common, a sine omega t take common. So we get here 1 plus cos phi and also plus this is a cos omega t and sine phi, a cos omega t and sine phi. Now let us assume 1 plus a into 1 plus cos phi is equal to or cos alpha or cos alpha. So a sin phi is equal to r sin alpha. So let us assume this equation as 1 and this equation is 2. Now SBS, equation 1 and equation 2, squaring on both sides. So what we get here, a square into 1 plus cos phi whole square is equal to r square cos square alpha. This equation is assumed as 3. Now a square into sin square phi is equal to r square sin square alpha. This equation is assumed as 4. Add 3 and 4 equation. What we write here, a square into 1 plus cos phi whole square plus a square sin square phi is equal to r square cos square alpha plus r square sin square alpha, that is equal to, we write r square. So here a square into 1 plus cos square phi, okay, plus 2 cos phi plus a square sin square phi is equal to what we write here, r square. So multiply with a square plus a square cos square phi plus 2a square cos phi plus a square sin square phi is equal to what we write here, r square. See, this a square cos square phi plus a square sin square phi, that is equal to a square. So a square plus a square plus 2a square cos phi is equal to what we write here, r square. So here this is 2a square into 1 plus cos phi is equal to r square. So 2a square into, here 1 plus cos phi means what we write here, 2 cos square phi by 2. This is the resultant amplitude, square of the resultant amplitude. So that is nothing but intensity of light. That means I proportional to r square. Okay. So this is known as here I, resultant intensity. So here I is equal to what we write here, 4a square cos square phi by 2. So I is equal to here 4 I naught cos square phi by 2. A square is the amplitude cell. So I naught is nothing but initial intensity. So here I is equal to what we write, 4 I naught cos square phi by 2. So this is the resultant intensity. At point P. when two light waves are superimposed each other. Now we are going to discuss about condition for bright bands. Condition for bright bands. Condition for bright bands. So obtain the bright band cos phi value, cos square phi by 2 value becomes 1. So such cases are phi is equal to 0. The phase difference between the two waves is 0 or 2 pi or 4 pi, 6 pi, so on to n pi. Then we see bright band at P. Path difference. The phase difference, the path difference between the two light waves is 0, lambda, 2 lambda, up to n lambda. We get a bright band at P. Already I explained what is the phase relation between the phase difference and path difference. Phase difference is equal to 2 pi by lambda into path difference. If we substitute phase difference 2 pi, we will get path difference as lambda. Now we are going to discuss about condition for dark bands. Condition for dark bands. Condition for dark bands. With the phase difference, so for condition for dark bands means here the resultant intensity at point P should be 0. Should be 0. So such values are phi is equal to pi, comma 3 pi, comma 5 pi, so on 2n plus 1 into pi. 2n plus 1 into pi. So that is nothing but what? Phase difference. So path difference, condition for path difference, delta is equal to lambda by 2, 3 lambda by 2, 5 lambda by 2, so on n plus 1 into n plus 1 into n plus 1 by 2 into lambda by 2. So if the path difference is like that, then we will see dark bands on the screen. So here we will see graph between intensity and the phase difference. So if the phase difference is 0, then intensity of light becomes maximum. If the phase difference is pi, the intensity of light is minimum, and 2 pi it is maximum. So in interference, there are bright and dark fringes are formed on the screen, which are having equal width. Now we are going to derive fringe width. Fringe width. These fringes are called interference fringes. The distance between any two successive bright bands or any two successive dark bands gives fringe width. It is denoted by beta. So here in triangle S1 S2, this is nothing but here Q. This point is Q. S1 S2 Q. Sin theta is equal to what we write here. Sin theta is equal to opposite side by hypotenuse delta by d. Okay. So if theta is very small, then sin theta almost or equal to right theta. So theta is equal to delta by d. Equation 1. Now in triangle here, this is nothing but this point is nothing but R. PRO. Sin theta is equal to what we write here, sin theta almost are equal to tan theta, that is almost are equal to theta. So tan theta is equal, we write here, x by d, theta opposite side x by d. If theta is small, so sin theta almost are equal to tan theta, that is equal to theta. So this theta is equal to what we write here, x by d. This is equation 2. So from 1 and 2, we write x by d is equal to what we write here, delta by d. So here x is equal to delta d divided by d. So here x is means what? X is nothing but position of dark or bright band from the center of the screen. From the center of the screen. So now, so here, now we are going to write for bright band. For bright band, what we write here, x is equal to. For bright bands, what is the path difference here? N lambda d by d. N lambda d by d. Right. So here, or in some textbooks, they use letter m. Okay. Position of the first bright band from the center of the screen, that is lambda d by d. Position of the second bright band from the center of the screen, 2 lambda d by d. The distance between these two successive bright bands, that is x2 minus x1, that is equal to 2 lambda d by d minus lambda d by d minus lambda d by d is equal to what we get here? We get here lambda d by d. This is known as fringe width, that is beta. That is a beta. Similarly, we calculate for dark band. For dark band. For dark band. So x dark. X dark is equal to here. X dark is equal to what we write here, delta d by d, but x dark is equal to, what is the path difference for the dark bands? For dark band, n plus 1 by 2 into lambda by 2 d by d. So this is the position of the dark band from the center of the screen. Now x1 is equal to, put n is equal to 1. So what we write here, 3 lambda d by 2d. 3 lambda d by 2d. 3 lambda d by what? How much? 2d. x1 is equal to. So now here x2 is equal to second bright band, put n is equal to 2. So 5 lambda d by 2d. Now take the difference, x2 minus x1 is equal to 5 lambda d by 2d minus 3 lambda d by 2d. That is equal to what we write here, 2 lambda d by 2d. That is equal to lambda d by d. Lambda d by d. So here also the width of the dark band is nothing but lambda d by d. Here in the previous case, the width of the bright band also lambda d by d. So bright and dark bands are having equal width. Having a equal width. So in interference, there is no loss of energy. So there is no violation of conservation of energy. So we know that here intensity is equal to I equal to 4I0 cos square 5 by 2. Cos square 5 by 2. We know that average value of cos square 5 by 2 over one cycle. Over one cycle is 1 by 2. So here I is equal to what we write here, 2I0. That means Here, the intensity of bright band, the intensity of a bright band is 4I0, whereas the intensity of dark band is 0. Dark band is 0. But average intensity, I average, but average intensity is average intensity of all fringes is same. There is no change in average intensity. So in interference, light energy is redistributed. Light energy is redistributed. That means here, if it reduces in one region, and forms a dark band, it increases in another region and forms a bright fringe. If it reduces in one region and forms dark band, it increases in another region. It increases in another region and forms bright band. So there is no violation of energy. There is no violation of law of conservation of energy. There is no loss or gain. In energy. There is no violation of conservation of energy. So this interface phenomena we can conclude that it supports law of conservation of energy, and the same thing will happen in diffraction also.